Hey, I've got a student already, Brian. Hey, Brian. And I also have another student, Dawson. Hey, Dawson.
Hey, how are you?
Terrific. It's a beautiful day out there, or at least it was when I went out to feed my dog this morning. Okay, we're going to do thermo now. I'm through with this class, and we're going to do thermo. So what is the topic today? Oh, hey, there's some students. There's Taylor. Yeah, howdy.
Hey,
Howdy,
how's it
howdy.
going?
There's Bryce. Howdy,
Hello.
howdy. Great to see you. But let me remind myself what we're going to do now. Let's put it this way. Let me see who's on board here. We've got, we got a big crowd. We got Alex, Braxton, Brian, Bryce. We have Mohammed and Nicholas and William, Taylor and Reagan.
Yes.
Got a great class here. And I think Noah, I think I saw Noah there. Maybe. Anyway, we got a great group. And what are we going to study today is the question. Well, do you have any questions before I figure out what I'm going to do? Do you have any questions?
Not offhand.
Okay.
I think I do have a question. This is Reagan.
Say that again, please.
Yeah, I mean, this is Reagan. I think I have a question on.
Is this the? I didn't hear you. I'm sorry.
I said this is Reagan.
Is this the Radian?
I mean, I have a question on homework.
Okay. Yeah. Sure. Which homework is it?
I think I did email you what exactly I was expecting to get from the homework grade, but you didn't email me back yet. So I'm just a reminder on that.
Oh, I'm sorry. Now, tell me your name, please.
My name is Reagan.
Okay, Reagan. And Reagan, you have a question about the homework, right?
Yes.
What is your question?
My question is the way you grade the homework. I just got confused, like, to see the grade. I don't know what exactly are you expecting on the homework.
Oh, okay. Well, if you got a 4, you made me happy, Reagan. You did what I wanted.
I
If you
think
got a 3, there was some little thing that wasn't quite right. If you got a 2, I give a 2 if you made an effort. Okay. So whatever grade you got, it's either a 2, 3, or a 4 on your grade. But I'll discuss any particular problem if you want. Do you have a problem number that you wanted to talk about?
Yes, I want to talk about those interpolation table, the one you did last time.
Yeah.
Yes,
Yeah, the interpolation tables.
Yes, I think I did not understand exactly what you.
Oh, I know what you're talking about. I gave you an interpolation worksheet, didn't I?
Yes, you did. Yeah.
And I have that here someplace. Let's see if I can find it.
Okay.
I've got it here someplace. It's an interpolation worksheet. Okay. Oh gosh. I can't seem to find it, but I think I had like 4 or 5 or 6 interpolation problems for you to do, right?
Yeah.
Tell me which one you had trouble with.
Yeah,
We'll do it.
I think on the homework I got 3 out of 4. So
Oh, okay.
so I
So
did
one of them wasn't right.
so I did show my work on all of them, but
Yeah. Well,
um
which one did I mark? Did I tell you the number of the one that was wrong?
no, you didn't put any comment on that. That's why I got confused. I was like, where exactly?
Okay. Well, I have them here. I finally found them.
Okay.
Several people had trouble with this number 3. There were 5 problems,
Mm-hmm.
and these are interpolation problems. I'll do one of them, and then we'll move on. Now, to get these, you have to click on the link that I provided. And there's 5 problems. We could just do number 3 together. They're all very similar. This is number 3. Specific volume and specific internal energy for superheated vapor water at 400 Celsius and 8750 kilopascals. I think I'm talking to Reagan, aren't I? Reagan, am I still talking to you?
Yes, I'm still here.
Yeah. Now, do you remember trying to work this problem, number 3, Reagan?
Yes, I remember, but it seemed like the way I did it was, I don't know if it was wrong or was correct.
Yeah. Well, here, let's just do this one together.
Okay.
If you didn't get a 4, there was something wrong with your paper there. But we're going to do this one together. Now, I need to explain to you about superheated vapor. Let's see if I can explain that. I need to explain to you, all of you, I'm talking to everybody now. I just pinned somebody. I pinned Bryce. Okay, well, I don't know why the pictures are showing up, but that doesn't hurt anything, I guess. Yeah, there we go. We're talking about the PV diagrams. The key to this class is the PV diagram. Let me explain that, and then we'll do this problem here for Reagan. All right, you've got a kind of like an XY axis, only the Y-axis is pressure, and the X-axis is specific volume. Remember, this is in units of cubic meters per kilogram. It's called specific volume. And this is pressure. It's in kilopascals. And that's pressure. And what they did was they plotted up some isotherms. They took a piston cylinder, with some steam in it, some H2O, but it's steam, okay? It's a vapor. They made it hot enough to where there's no liquid, it's a vapor. And they're going to do a process at a constant temperature. So we're going to draw an isotherm on here. And the way they did that is they put this in a big, like a bathtub of oil, of hot oil. And let's just suppose it was 200 degrees. We'll just make that up. 200 degrees, okay? Now our problem is 400 degrees, but we'll get to our problem in a minute. Okay. And so you got a pretty big volume out here, and the pressure is fairly low. We'll locate it. I'm just making this up. We could look in the tables and find it, but we'll say it's there. And we'll say the pressure is there. Now here's what we're going to do. We're going to take that and we're going to put a weight on it. So later, here's your piston. It's in this hot oil, but we put a weight on it. Now when you put that weight on it, the volume goes down and the pressure goes up, like that. See, the volume got smaller. It's specific volume. It's volume per mass. Can you see the volume got smaller? And can you see that the pressure will go up if you put a weight on it? Actually, they did, and they kept the temperature the same, the 200 degrees Celsius. And they kept adding weight onto it until something interesting happened. It started to condense in the piston, and some liquid started to form. And we can call this state 3 if you like. Here's your piston again. And the volume goes down even more, and you add a little bit more weight to it, maybe make it a little taller. And what happens is you get some liquid here. You'll still have vapor in there, but you'll get some liquid. It's condensing. It's the opposite of boiling. And condensing and boiling occur at a constant temperature. And so the volume doesn't change. I'm sorry, the temperature doesn't change, and the pressure doesn't change. What am I trying to say? Boiling and condensing are isobaric. They occur at the same pressure. And then what happens is eventually you're still at an isotherm. You're still at 200 degrees Celsius. But your piston is down here now. And it's all liquid. You reach a place where it's all liquid. Then if you continue to add weight to it, the pressure goes sky high, because liquids, they don't change their volume any. They're, what's the word? Incompressible. Now, the truth of the matter is liquids do compress just like solids do, but it's very little compared to gases. And so you get a curve like that from an experiment at 200. This is your 200 degree Celsius isotherm. And then they do one at a higher temperature, a 300. Let's do the 300 degree Celsius isotherm. It kind of goes like this, and it condenses here. There's your 300 degrees Celsius isotherm. They do this experiment over and over. Then there's a place, I think it's 374, where it comes up, and there's an inflection point, but it really doesn't ever condense any. And if you had some lower temperatures like a 100, let's say there's a 100 degrees Celsius isotherm down here, it kind of goes like this. In other words, I'm telling you, they made a lot of experiments at constant temperature. They can control that by putting your piston in a oil bath and keeping that temperature constant. Then what they did was they saw these places where it's a dividing line in your state between liquid and a liquid vapor mixture. And they connected the dots. And here's what they get. They get something kind of like this. And they call that the vapor dome. They obtain that vapor dome by experiment. Inside this vapor dome, you have what they call saturated mixture. You have a mixture of liquid and vapor. See here, you've got liquid and vapor. Over here, once you reach this point here, it's all liquid. And the fancy name for this is compressed liquid. Here, out in here, there's no liquid at all. It's all vapor. In fact, they call it superheated vapor. That's the name of it. Now, this dividing line between superheated vapor and saturated mixture is called saturated vapor. And this dividing line here between all liquid and a mixture of liquid and vapor is called saturated liquid. At the very top of the vapor dome, they call that the critical point. I've just tried to explain to you guys the PV diagram. Now there's pictures of it in your book. Let me see if I can find you a picture of this in your book so you can look and see what I'm talking about. Okay. Yeah, I see some. There's many pictures in chapter 2. One of the best ones is on page 36. If you look at page 36, you'll see a three-dimensional thermodynamic diagram that gives you not only the pressure and the specific volume, but the temperature also. It's really three-dimensional. But that's how they obtained it. They obtained it by taking many experiments, pressure. Okay, now that I've explained that, we're gonna do our problem here. It's an interpolation problem. It's number 3. But before I do you have any questions so far? Well, okay. If you don't have any questions, we're going to do our problem now. But I wanted you to understand, where did this thing come from? There's a picture of it on page 36. It's called a, well, actually, that's a PVT diagram. It's got all 3. But we're just looking at the PV part of it. Okay. Now we're going to work this problem. And to do it, we're going to go to our tables. And here's what you always do. You draw yourself your vapor dome, and it kind of looks like that. It's pretty steep on the left and pretty gentle on the right. And in this number 3, it's steam. So we're going to go to the H2O, the steam tables. Let me find them here. And I found them. Yep, here they are. And you always go to the saturated table first. Now we need 400 Celsius. And do you notice on table B.1.1, the top, the hottest temperature they have for your vapor dome is 374.1. Now what that is that they call that the critical isotherm. It goes like this. That's your 374.1 degrees Celsius isotherm. Now the pressure right here, they call that the critical pressure. That's 22,089. You really need to be on table B.11 to find that number and define that number. I'm going to wait until I hear some students say, yeah, I found it.
Mr. Griffin, are we
Can
doing
you find, did you find it?
no, are we doing superheated vapors, but that table is for the saturated water.
Yeah, this is water.
But on the number 3, we have superheated vapors, not the saturated water.
Right. But I want you to go to the saturated chart first.
Oh, okay.
See, we have 400 Celsius, but thank you for mentioning that. I know it's confusing, but if you'll go to the saturated chart first, it'll help you locate where you are. Now we're at 400. So 400 is out here like this. Here, let me scoot that out of the way there. This is your 400 degrees Celsius isotherm. Now, they've got to give you something else. Oh, they say superheated vapor, water at 400. They have to give you something else. Just a minute. I lost my sheet. Here we go. Yeah, here we go. They also give you, it's 8750 kilopascals. Okay. Well, you know what? 8,000 is smaller than 22,000. It's kind of down here someplace. 8,750 kilopascals. So I tell you where we are. We are right here. Call it state 1, if you like. That's where we are. We're at 400 Celsius, 8750 kilopascals, and we're in what they call the superheated vapor region. That stands for superheated vapor. Now we have a superheated vapor table. So let me find that. I'm going to dig around and find that. Aha, I found it. Now what I want is the 8750. Well, they don't have an 8750. I tell you what they have. I need some room, so I'm going to put it up here. They don't have 8750, but they do have they do have 8,000, and they do have 10,000. So let me write those. At 8,000 kilopascals and 400 Celsius, the specific volume is 0.03 432. Now I'm on table, this is table B.1.3. B.1.3. See if you can find it. Now those are cubic meters per kilogram. Now they don't have an 8750, but they do have a 10,000. So let me write that. At 400 Celsius and 10,000 kilopascals, the specific volume is 0.02641. 0.02641. Okay, great. We've gotten all that stuff from the tables, but see what we want is 8750. So it's between 8750 is between 8,000 and 10,000. We need to find out what percentage of the way 8750 is from 8,000 to 10,000. Well, I can do that. There's a difference here of 2,000 kilopascals, but from here to here, it's just 750. So we take 750 divided by 2,000. You know what? To get from here to here, you have to go 37.5%. Let me write that down someplace. We want to go 37.5%. That's how far it is from 8,000 to 8750, from 8,000 to 10,000. What we need is 37.5% of this distance here. Okay, well, let me do that. I'm going to take this distance here. Probably should write it here. Let me write it. I'm going to take 0.375% times this distance here. 0.03432 minus 0.02641. And what I'm going to have to do, since these numbers are getting smaller, is I'm going to have to subtract that from the 0.03432. That's going to be my answer. That's going to be the missing V here. We're trying to find the specific volume. Well, this is how you do it. You take the 03432 and you subtract 37.5% of the difference between here and here. All right, I'm going to do that. Here goes. Times 0.03432 minus 0.02641. That gives me that. Plus 0.03432. Well, I got an answer. Let's see if this answer makes any sense. I'm getting 0.03135. Now, is that answer in between that number and that number? Yeah. You know what? 31 is between 26 and 34, isn't it? Does it look like it might be 37.5% of the distance from here to here compared to the total distance? Yeah, it does. That's the answer. To problem 3, the answer is that now back, I think it was Mohammed that asked me this. Mohammed, did you understand that?
I think it was Reagan.
Reagan.
I'm sorry, Reagan.
That was me.
Reagan, did you understand that?
Yes, I do understand, yes.
And that's good. I feel good.
I have a question.
Go ahead.
So I ended up with 0.03729 And I know that that's like still pretty, I know like how, as far as grading goes, I was off by a little bit, but still like in the ballpark.
That's outside of here. Now tell me your name,
Taylor,
Taylor.
it's outside of where?
Well, see, the answer is going to be between
Oh, I
26 and
see.
34. You can't get 37. 37 is not in between 26 and 34.
You make a valid point.
Got it.
Sir, I have a
You
question.
know what you did? It's Reagan. I'm talking to Reagan, right?
I'm Taylor. I was one that asked the last question.
I'm so sorry, Taylor.
Uh-huh.
What I know what you did, you added, but see, these numbers are getting smaller. You added.
Oh, you're right.
That's what you
Okay.
did.
I certainly did.
We got to learn how to use these tables. Okay, good. Well, we played with that. And I'm trying to show you about the PV diagrams. By the way, the PV diagram is the soul, the heart and soul of our course. Unless you can master the PV diagrams, you're going to have trouble. So I thought I'd tell you that up front so that you can know what's coming. We've got to learn those.
Hear me?
Okay, now what's next? Let me see what I want to do next. I've got more to do than we have time to do, but let's try this one. What we're doing today is PV diagrams is what we're doing. And to review, let me see if you guys paid attention. They call this region out here the SHV. SHV. Now let's see if anybody can remember what that is. I'll pick on William. William, unmute and tell me what SHV is.
It stands for superheated water vapor.
That's it. Well, it's just superheated vapor, William, because it could be R12 or R134A or ammonia or 100 other things, okay? It might not be water, but that's what it is. Now, inside here, this is S dot M dot. Let's see if this person listened to me earlier here. Tyler, unmute and tell me what S dot M dot stands for.
Is it saturated? Where is it?
You got half of it. It's saturated something. Good going, Tyler. Saturated. I'll give you a hint. It's part liquid. You got part liquid and part vapor. So when you have two different things, what do they call that?
Saturated mixture.
That's it. It's a saturated mixture. Good going, Tyler. As long as I'm talking to Tyler, if you're on this line here, it's got a very special name. It's called S dot V dot. Tyler, what's that stand for?
Saturated vapor.
That's it. If you see saturated vapor, you're on that line. Okay. And see, we have tables for these things. We have a table for superheated vapor. We have a table for saturated mixture. Now over in here, that's C dot L dot. How about my friend Taylor? Now we were talking to Tyler. No, that was Taylor. Let's go to Noah. Noah, we'll see if you can remember the name of this C dot L dot. What do you think it is, Noah? He's thinking.
Let's see. does it have to do with condensation?
Well, when you're over here, it's all liquid. It's all liquid. See, here you have part liquid, part vapor. Out here you have all vapor. Here it's all liquid. And that C dot L stands for, what do you think?
Probably something liquid.
Yeah, you got that right. It's called a compressed liquid. Compressed. Remember my experiment thing where they kept adding weights to that piston and they kept
Right, and the liquid.
they're compressing that. You compress it and you compress it. And if you do that enough, you'll get to the place where it's all liquid. There's no vapor. The vapor's all been condensed and it's all liquid. Now, if you go from liquid to a vapor, I know you've done this in the kitchen. You put some water on in your pan, you turn on the fire, and you go from all liquid to all vapor. I'm going to call on somebody. This will be fun. Let's go to my friend. We're going to go to my friend Braxton. Braxton, unmute and tell me if you start with all liquid in your kitchen, in your pan, turn on the fire, and it's all liquid, and then it'll take a while, but if you leave it on that stove long enough, it'll be all vapor, all the liquid's gone. Braxton, what do they call that?
Evaporation.
Yeah, that's the fancy word, and you're absolutely right, Braxton. But what I was going to call it is boiling.
Oh yeah. Okay.
It's just boiling.
Yeah.
To go from here to here, it's boiling. But hey, there's nothing wrong with the word evaporation. Right. It's evaporation. Now if you go from all vapor the other way, and you go to all liquid, we'll pick on Braxton again. He did good on that first part. But what do they call that, Braxton, when you go from all vapor to all liquid? It's got a name. It's called what?
Precipitation. I don't know.
That was pretty smart. Guess. I'll give you a hint. It starts with C.
Oh, compression?
Well, it is. You could think of it as compression. However, this is an isobar. And the word I wanted was it condenses. It's condensation. See, when you put an ice cold Coke or iced tea on the kitchen table there, you'll notice after a while, you lift it up and there's a ring of water there. It's condensed because it's cold and there's water vapor in your kitchen air and it hits that cold Coke or iced tea there and it condenses. It condenses at constant pressure because the pressure inside your kitchen hasn't changed any. Just because you put a cold Coke on the kitchen table, the pressure inside your kitchen stays the same. It's an isobaric process, but it's called condensing. And you go from vapor, water vapor in the air, to liquid on your kitchen table. I know you've seen that. Haven't you seen drips of liquid on the bottom of a cold glass?
Yeah,
Yeah, you have. Sure you have. Okay, well, we're trying to learn how to do these PV diagrams, and I want to do another problem now. This one is, I think it's 238. Let's make some room and do that. Say goodbye to all that wonderful stuff there. I believe the one I picked out is 238. Okay, now let me find it. Hang on a minute here. 238. Yeah, I found it. Okay, now this is R410A. Now that's what I've got in my house air conditioner. I've got R410A, and they said it's at 60 degrees Celsius, and it has its pressure to decrease to increase the volume by 10% while keeping the temperature constant. So we're going to have an isothermal process, and we're going to draw the 60-degree isotherm, and we're going to decrease the pressure. Yeah, and the volume will increase 10%. Okay, they want to know what the new pressure is. Now, the first thing you got to do is find R410A. Go to the back and shop around and help me find R4. Hey, I found it. Now, always go to the saturated table first. It might be that we're not in saturated in the vapor dome, but I like you to go there first anyway. Just do what I tell you for a while. And we're going to draw our PV diagram now. Okay. And remember how it goes. It comes up here pretty steep, and then it gradually tapers off. And let's put some numbers on there. I'm on table B.4. Table B.4. And what we're learning today is we're learning PV diagrams. That's what we're learning. PV diagram. Probably the most important concept in our course is the PV diagram. Now, I can tell you what this top pressure is. It's, I'm on table 4.1. That pressure right there is 4901. 4901.2 kilopascal. Okay. Messy writing there. And the specific volume right here is 0.00218. Okay. And the temperature is 71.3. And now that's the critical temperature, 71.3. Now, before we go on and work our problem, I want to know if you can find those three numbers, the 4901 and the 00218. And the 71.3. Can you do that?
I got a question for you, Professor.
Yeah, go ahead.
Well, I'm looking at the temperature. It says 71.3.
Yeah.
For the numbers that you have. Yeah. I'm a little bit confused by that. I thought it said 60 degrees.
Oh, well, see, we haven't even started this yet. We're just getting the lay of the land now. We're getting kind of like the boundaries here. We haven't found our house in the neighborhood. We're just looking at the streets, okay? And the different houses and the stores. We're just getting a feel for this. See, we're going to get to the 60, but let me tell you where the 60 is. Now, who was that just asked me that?
Nathan.
Nathan? Was it Nathan?
Yes. Yes.
Thank you, Nathan. Thank you for speaking up. 60 is smaller than 71, but I'll tell you where it is. It's kind of towards the top. It's sort of like this. And remember, when I told you what these do, this is a constant pressure condensation. That's the 60-degree Celsius isotherm. We're on that. We're on the 60-degree Celsius isotherm someplace. But now where is the question? Well, let's read the problem again. I kind of got lost. Let me find the problem. 238. I think I lost my place. Okay, there it is, 238. Oh, they said saturated vapor R410A. Hey, we know what that is. Saturated vapor. We know where we are now. We're right here. Here's state 1. Isn't that saturated vapor? Remember, this is saturated mixture. This is superheated vapor. But saturated vapor is anything on this line. And we have to be on the 60-degree Celsius line, don't we? I wonder if I've lost anybody or if you're still with me. There's
I'm a little
state
lost.
1. Oh, hey, wait a minute. Who was that?
Taylor.
Taylor, are you lost, Taylor?
A little bit. I see on the table that you took down the stats for the 71.3 degrees Celsius.
Yeah.
I guess that's where the disconnect is because they have data for 60 degrees Celsius on the table.
Now, Taylor, there's hundreds of isotherms on here. There'll be one here at, say, 40.
Right.
And it'll go like this. Sorry, it wiggled there. And there's hundreds more. All I did was I wanted to show you that this is called the critical isotherm. It's at the top of the hill. We're not at the top of the hill. We're on the side of this vapor dome. We're right here at saturated vapor at 60 degrees Celsius.
And how do we know that 71.3 is the critical temperature?
Oh, thank you for asking. Look on appendix table B.4. Can you find that B.4?
I'm looking at it.
Good. And look at the hottest temperature on the page. What is it?
71.3.
Yeah, that's how come I know it. See, this is the vapor dome table right here. That's as hot as you can get and still be anywhere near the vapor dome. Okay?
Okay, so if it's the
Now
hottest temperature on the table, then that's going to be the critical temperature?
That's the top of the hill. But we're not there. We're here at 60.
Is there a table that you're looking at in the book to know that you're at the top of the dome, or a graph rather?
Yeah, you just looked at it. You just found the 71.3. That's the table. It's table B.4.1.
Correct. I was asking if there's a figure of the graph that you've drawn here in the book somewhere. I have the online version, so it doesn't really fold out like the book.
Well, they have many pictures of these PV graphs throughout the book.
But
And,
specifically this one, you're drawing yourself. You're not referencing anything from the book, correct?
No, it's kind of like people, there's millions or billions of people. We're all different.
Gotcha.
And so-
Okay, I'm on the same page then.
Yeah. Yeah, we're okay. We're all different, right?
Right.
We're all different. Okay, but now that's state one. Now, if you read the problem though, they said they're going to do something. They're going to increase the volume while keeping the temperature constant. Okay, well, how are they going to do that? Well, I think what they're going to do is they're going to follow this isotherm, and that'll keep the temperature constant. And here will be state two down here someplace. Now, how are they going to do that? Well, they're reducing the pressure. Here, I'll draw you a picture. Here's your state one. And you have some weights on here, okay? There's state one. And it's 60 degrees Celsius. And how are you going to keep 60 degrees Celsius? Well, that's where that bath comes in. Put it in an oil bath that's a bathtub. Fill your bathtub up with oil and stick your thermometer in there and somehow heat it up to 60 degrees. But here, what happens here is you take some of that weight off. Now, when you take that weight off, the volume goes up. You're still in the oil bath. You've still got 60 degrees Celsius. But see, the pressure goes down. The pressure was here. The pressure was, let me tell you what the pressure was. It was 36.9. See if you can find that. Kilopascals. See, when the temperature is 60 and you're saturated vapor, the pressure is 36.9. If you can find that table, B.4.1, that was your pressure. But see, we're going to lower the pressure. I think this is what they want to know. They want to know what P2 is. But see what happens when you lower the pressure, you take some weight off. Hey, it expands. Can you see that? The volume goes from this volume here, which is, by the way, I can tell you what that volume is. It is 0.00497, I believe. 0.00, yeah, that's it. You really need to pull up this table to get that volume. That's your specific volume at state one. Now, if you read the problem, they want you to increase the volume by 10%. So we can do that. The volume at state two would be 110% times the volume at state one. Well, we got the volume at state one. Do I need to explain how I got the 0.00497? Anybody lost on that?
Yes, I'm lost on that.
Okay. Can you get to table B.4.1?
Yes, I am.
Okay. I want you to look at 60 degrees and go over here to where it says V sub G. It'll say V sub G. See that little VG?
Yeah, I got it.
Everything on this line here is a VG. You could think of it as a gas, G for gas.
Okay.
Everything on this line is a VF. You could think of it as a fluid.
Okay.
Can you find that?
Yes, I find it.
Excellent. That's where I got it. Now what we're going to do is we're going to increase the volume by 10%. All right, well, here's going to be our new volume. Here goes. We're going to take 1.1 times 0.00497. Well, I got an answer. I'm getting 0.0054667 cubic meters per kilogram. See if you don't get that. Now we have V2. Now here's what we know at V2. We have the specific volume. I'll circle that because we have it. We have the temperature at state 2. It's 60 degrees. It hasn't changed any.
I have a
Comment
question.
or question? Yeah, go ahead.
So on the graph, it looks like is the volume not decreasing, but we got a
No, it's, guys, here's the way graphs work. When you go this way, like if it's an x-axis, you're getting bigger, you're getting bigger, you're getting bigger. If you go this way, the V's are getting bigger. Look, at the volume is bigger at state 2.
Okay, that makes
Get
sense.
it? It's getting bigger. And here's the new volume. Look, 005 is bigger than 004. Yeah, the volume's getting bigger. Okay. Now here's the thing. We know V2, we know T2, and what they want is P2. We don't have that. That's what they want.
Mr. Griffin, how you get that?
Here, go ahead.
How did you get that 1.10 V1?
Oh, that's if you increase something by 10%. Let's say you make $100 a week for tutoring thermo students. If you want to increase that by 10%, what you do is you multiply by 1.10. Isn't that how you increase something by 10%?
Oh, okay, got it.
So you would see, then you would get $110 per week.
Got it.
You must have added another student to the tutor. Did that make sense?
Yeah, got it.
Thank you for asking.
You're welcome.
All right, anytime. Now, what we got to do is we got to figure out this new pressure. See this new pressure, P2? We don't know what it is, but it's in the superheated vapor region. So guess which table we use?
Superheated vapor.
Yeah, we use a superheated vapor. So flip here to the R410A, which stands for refrigerant, 410A. It's what I have in my house air conditioner. And we're going to have to find it in these tables. All right. I need a little room here to work. And here's where we get to interpolate. We want 60 degrees Celsius. We want specific volume 0.05467 cubic meters per kilogram. Okay. Now we're going to go to our tables. And we know the pressure is smaller than 3836. Can you tell that? See, the numbers get smaller. They get bigger going up and smaller going down. So we're going to find a pressure in the superheated vapor table smaller than 3836. And how about 3000? Here's what we got. At 3000 kilopascals and 60 degrees Celsius, the superheated vapor table says you have 0.00858 cubic meters per kilogram. Now see, we already know at 3836.9, let me write that down, 3836.9 kilopascals, we already know that that specific volume is 0.00497. because we looked it up. That was V1. See, what we want is a specific volume of 0.05467. Can you see that 0054 is between 0049 and 0085? So our answer will be between 3836 and 3000. Did that make sense? We've got to interpolate. We're going to interpolate now. See, at 3000, how did we get this 0.00858? We looked in the tables. This is table B.4.2. I found that in the superheated vapor table. Because see, we're in superheated vapor. How do we get this 005? Blah, blah, blah. Well, we multiplied 1.10 times V1. Well, how do we get V1? This is V1. How do we get that? We looked that up in the saturated mixture, or I call it the vapor dome table, but the book calls it the saturated mixture table. Do I need to go back and show you where those are in the tables, or are you with me on this?
I'm following.
Well, all we got to do is interpolate. Can you see that 49.85? 54 is between 49 and 85. So our answer is going to be between 3,000 and 3836. All right, let's do it. Here goes. I need to know what the percentage is to go from here to here versus from here to here. I'm going to do that now. Here goes. All right, I'm doing that now. I'm interpolating. Well, I interpolated and I found that I'm 87% of the way, 86% of the way to get from here to here. Those numbers are actually getting smaller, and I have to go down 86.2% of the way from. It's kind of like you have a salary and you drop 86.2%. That'd be bad, wouldn't it? It's kind of like if you make $100 a week and you drop 86.2%. Now what do you make? $13.8 because you've dropped 86%. Holy cow. Okay, so what we got to do is we got to drop 86.2% of the way from here to here. But wait a minute, now these don't drop, they get bigger. We have to take this difference, which is 836.9, and multiply it by 86.2. So I'm going to do that now. And then what you do is you add it to this. And what I'm getting is 3,700, and I'll just round it off to 22 kilopascals. So our new pressure here is 3,000 722 kilopascals. Well, that's it. We did the problem. We did 238. I'll go back over any part of it that you want. It was kind of hard, wasn't it? And floor is open for your questions. Anybody have a question? I'll try to answer it.
Can you kind of just summarize the steps? Not redoing it. I'm not asking for that, but just kind of like you went to table such and such to find such and such, and then from there.
Yeah.
You know
Yeah.
what I mean?
Okay.
That might help me.
Well, the real. Tell me your name again.
Nathan.
Nathan. Okay, Nathan. You've got to draw a PV diagram. There's your P, there's your V. You got to draw the vapor dome. You've got to locate your state one. State one, they said, was saturated vapor. Didn't they? Well, let me read it. Yes, saturated vapor. You got to know what that means, Nathan. It means you're on this line here. So we know we're on that line. Now they said it's 60 degrees Celsius. I kind of know where that is. Because see, the very top of the dome is, I erased it, but it was 70, I think it was around 71 degrees, something like that.
71.3.
Yeah, there you go, 71.3. So it's kind of towards the top. It's not down here towards the bottom. It's kind of towards the top. 60 is fairly close to 71. So I drew my isotherm. There it is. There's the 60-degree isotherm. That's what they look like. They pretty much go kind of vertical here. That's because the liquids don't compress much. The volume doesn't change much when you increase the pressure on liquids. In fact, they don't even slant that much. They're pretty much straight up. So there, and this is your evaporation, and this you're in the superheated vapor region here, and there's your. I tried to explain how they got those isotherms with that water bath in your bathtub with the oil.
So within the question itself, it'll give you terms like saturated liquid or saturated vapors that'll tell you what tables you would need to look at.
Yes, Nathan, you got to find your state one, and then you have to figure, well, what's the process going to be? Well, there's all kinds of processes. There's isobars and isocores and polytropic processes. Gosh, I can't remember. Have we done polytropic processes?
No, sir.
We need to. I think that's definitely coming up. But see, we know what this process is. It follows the isotherm. It's an isothermal process. We know we're getting a volume that's bigger. How do we know it's bigger? Well, because they said so. They said the volume is getting bigger. If you read it, it says increase the volume. Yeah, okay, so the volume's increasing. There you go. How much is it increasing? Well, they said increase it by 10%. So we did that. And then you look up the V1, the specific volume at state 1, multiply it by 110%, and you get the specific volume at state 2. It's bigger. And you draw your process. See, this is your process. It happens to be an isothermal process. Okay, and then what? Well, we know a lot of things. We know the temperature. We know the specific volume. We know we're in superheated vapor. So you go to the superheated vapor table. And I wrote down what we know. We know at 60, No, wait a minute. Yeah, at 60 and 3,000 kilopascals. I got that from the superheated vapor table. I got lost. Oh, at 60 and 3,000, that's the specific volume. And then at 60 degrees Celsius, and this was the original specific volume, and that's the original pressure. See, this is P2. That's state 2. This is the specific volume at state 2. It's bigger. And what we did, we had all these numbers, but we didn't have this number. We had to interpolate it. The key is this PV diagram. Let's do another problem. We got 10 minutes. We're going to use it. Here goes. But was there anything else?
That helped. Thank you.
No, anytime. Yeah, that's what we're here for. Okay. Here's what I want to do now. Yeah, this is, I'm going to say goodbye to this problem. That was a lot of fun, wasn't it? Wasn't that fun?
It was a blast.
That was a blast. We got 10 minutes, but this will be easy. And it's problem 234. Problem 234. And they said, oh, it's 410A again. No, 224. I can't, I need to get glasses, my wife says. I don't want to get glasses. It's 410A. And they said, we're going to do A, B, C, D. We might have time to do all those. They said you have, for part A, you have 50 degrees Celsius and 0.005 cubic meters per kilogram. Now what they want to know is, where are we on that PV diagram? Well, we can do it. Here goes. I shouldn't have erased it. I should have kept it, but it kind of got messy after a while. Here's your PV diagram. We already did a 410A, and we knew that 60 was up towards the top. So 50 is a little lower than 60, but it's kind of up towards the top. There's your 50-degree isotherm. And now we're going to go, we always go to the saturated chart first. Help me find it. R410A. Okay, I'm trying to find it. I got lost. Yeah, there it is. And then we want the saturated chart. You always go there first. Okay, now this value right here is called VF, and it is 0.001103. Now this value right here, that's called VG, and it is 0.00707. Okay. Now, what we have is 0.005. You know what I think? I think 5 is in between 7 and 11. What do you think? I think we're right here. You want to call it state 1, maybe? Did that make sense?
Yes.
0.005 is between 0.001 and 0.007. And we're done. All they wanted on this was us to say you're in saturated mixture. Dead on, there you are. And they didn't ask for anything, but if they had asked for the pressure, I can tell you what it is. It is 3065.2. Can you find that? Can you find that 3065.2? Can you find it? You've got to look on table B.4.1. I need somebody to say, uh-huh.
Uh-huh.
Yay, that's what I wanted. Good deal. Okay, well, let's do B now. That's all they wanted us to do. Okay, now B, let me find it here. I got lost. B is, we're doing 224. And B is 1 megapascal and 5 degrees Celsius. 5 degrees Celsius, 1 megapascal. Okay. Well, let's find 5 degrees Celsius. Well, 5 degrees Celsius is a lot colder than 50 degrees Celsius. It turns out it's kind of in the middle of the vapor dome. Here, I'll fake it. This is the 5 degrees Celsius. And what else do we know about it? What else do we know about the 5 degrees Celsius here? Let's see. 1 megapascal. Okay, well, let's look and see. Now, this says at 5 degrees Celsius, that's supposed to be flat. If I could draw without sloping, it's supposed to be flat. Here, let me try to do a better job. That is supposed to be flat. Came out the same. That pressure there is 933.9 kilopascals. But see, what we have is 1,000 kilopascals. That's 1 megapascal. That's 1,000 kilopascals. You know where that is? That's right about inside. So you know where we are? We are on the 5 degrees Celsius line someplace. But to have 1,000 kilopascals, that's a little bigger. You're right there. You want to call that, what do we call it? B. That'd be a nice name for it. So the answer to B is compressed liquid. Oh, gee, we're running out of time. We got time to do C, and then we'll have to quit. C is, we're doing 224 right now. C is 0.1 megapascal. 0.1 cubic meter per kilogram. Okay. Well, now help me find that. You know what that is? That's 100 kilopascals, isn't it? Now I want you to look at the vapor dome table, saturated table for R410A. They don't have 100 kilopascals, but they have 101. That's way down pretty low. Here, I'll fake it for you. It's really cold down there. Minus 51.4. This is minus 51.4 degrees Celsius. Well, that's actually at 101. But it's pretty close to that. See, that's what it is at 101.3. I'm on table B.4.1. If you can get there, you'll find the 101.3 and the minus 51.4. But see, what we're at is 100. Well, 100 is a little bit smaller, so it would be not much. It's dang close. So our temperature would be a little bit colder even. I don't know, like maybe 52 or something like that. I'm just guessing. I don't have time to interpolate. We only have a minute left. But see, 100 is dang close to 101. You're right there. But let's just look up these numbers here. At that 101.3, we have 0.0007 41, and over here the VG is 0.23949. Now what do we have? We have 0.1. Well, you know what? 0.1 is in between 0.0007 and 0.2394, isn't it? It's over here. I don't know, over here someplace. Call it state C. How's that? The answer to this one is saturated mixture. We didn't get to part D, but that's how you do it. The key to this class is this PV diagram. And you have your homework, and it's due Friday at midnight, I think. Hey, our time is up, but it's been fun. Any last comments or questions from anybody?
Mr. Griffin, the next time, can you go over the problem 83E?
Yeah, we did that. That was chapter 1, 83E.
Yeah,
I would love to go.
Yeah, but next time, can you go over it in the next lecture?
Yeah, if you remind me.
Yeah, I
if
would
you
remind.
remind me.
Yeah.
I tell you what, I looked at your papers, and many of you did a wonderful job. I think you came in at, wasn't it something like 90 PSI maybe? Was it 90 or was it 600 PSI? I don't remember. Let me see if I have that. That was chapter 1, wasn't it?
Yes.
Yeah. And it was in the English stuff is 183. We're talking about 183E. Yeah, it was 90, wasn't it? You came in here at 90 PSI. And then you went into a pump, and you came out of the pump, and when you came out of the pump, I don't know, it's something like 253 PSI, something like that. I wonder if I have that. But anyway, I was proud of you. A lot of you got that right. I don't know if I can find that. Yeah, here it is. Coming out of the pump, it was 231.3. And I was so proud of you because a whole bunch of you got that right. But what they wanted is they wanted the difference. They wanted what the pump did to the water pressure. So if you take 231.3, you'll get 141.3 PSI. That's the answer they wanted. They wanted, what does the pump do? How much does the pump increase the pressure? It comes in at 90. It goes up to 231. So the pump increases the pressure by 141.3. And a lot of you did great. You just didn't subtract that. Any other comments or questions?
No, that's it.
Well, okay, have fun. I'll see you Wednesday. No, Thursday. I'll see you Thursday at what, 11? And this was on, this will be on YouTube. You can watch it over again if you want.
Did
So-
you upload the lecture from Monday already to YouTube?
My,
Zoom
I
was
bet
down on
my
Monday.
IT person did. I bet it's on there. But I
Okay.
hate to say yes for sure. She's very
No worries.
efficient. It'll be on there.
Thank you
Okay,
very much.
anybody else? Thank you very much. Okay, well,
Thank you.
adios, muchachos. See you,
Yeah, have a good day.
bye, you too.
Thank you. Bye.
Thank you.
Bye-bye.